Hello everyone, my name is Victor Zachary and today I'm going to talk about our work Cache on Track COT, Decentralized Elastic Caches for Cloud Environments. This work is in collaboration with Lawrence Lim, Divi Agrawal, and Amr Labadi at UCSB. So today's social network and web architectures consist of a distributed storage layer, which is persistent storage, deployed at the cloud, with a distributed caching layer deployed on top of the storage layer for high throughput and fast access. End users send their page load and page update requests to thousands of stateless and front-end servers, either in the cloud or the edge data centers, that serve these requests mostly from the cache layer and only if necessary from the storage layer. The caching layer uses consistent hashing to distribute keys across the caching servers, and front-end servers use the same hash function to locate the keys. However, workload skewness, mainly because there are keys that are hotter frequently accessed than others, cause load imbalance across servers in the caching layer. This results in long access latency and lower throughput. Previous work has proposed that having a small perfect cache where top C keys are known in advance and cached in the front-end servers reduces the load imbalance across caching servers. However, this work assumes perfect caching, a goal that is hard to achieve on dynamic workloads with changing access pattern. Also, this work assumes a fixed cache size for all front-end servers. In this paper, we propose cache on track, an elastic and decentralized cache at the front end to reduce the caching server load imbalance and enhance the access performance. COT answers the following question. 1. How to track hotkeys. For this, COT uses a space-saving algorithm to approximately track the top K, where K is greater than C keys at each front-end server. 2. What is the size of the small cache? COT is elastic, leveraging the elasticity of the cloud and dynamically expands and shrinks the tracker and cache sizes based on the observed workloads at each front end. 3. How to detect changes in workload distributions. COT dynamically monitor the hotness of the track and the cache keys to detect changes in the workload distribution. And finally, how to retire old hotkeys. COT dynamically monitor changes in the working set and triggers half-life time of hotness to forget retired hotkeys. COT's caching algorithm uses two min heaps. The first heap of size K is a tracker that tracks the hotness of access of K keys, where K is larger than C. When a key is first observed, it first goes in the tracker, and if a key becomes hotter than the minimum hotness of the cache keys, a key in the tracker evicts a cache keys and replaces it. Note that the cache stores the metadata of a key and the value, while the tracker stores only the metadata of a key. Also, a key hotness is calculated by the number of read accesses of the key times some read access weight minus the number of update accesses of the key times some update access weight. In our experiments, we set the read and update weights to 1. A key that is frequently updated should be evicted from the cache since updates result on cache invalidation. Unlike traditional cache replacement policies, where a key is first inserted into the cache and potentially evicts a hotkey, in COT, keys are inserted into a tracker until they prove they are hot enough to be cached. When they are hot, they evict hotkeys from the cache. COT is elastic, allowing for dynamic cache recycling. To determine the ideal tracker to cache ratio for some workload, we first fix the cache size and keep doubling the tracker size until the hit rate of COT over time epochs settle. Until then, once this happens, we know the ideal tracker to cache ratio for this workload. In COT, there is no centralized decision about which keys to cache and what front-end cache size is. Each front-end determines its contribution to the caching server load imbalance. Load imbalance equals the max load over the min load of caching server at this front-end servers. Load is determined as the number of requests sent to the back-end caching servers by this front-end server. System administrators have to provide COT with a target acceptable load imbalance IT, say 1.1. The resizing algorithms double the tracker and cache sizes until IT is achieved or an upper limit of cache is reached. For shrinking, check the paper for details. Now we present some of our experimental evaluation. YCSB Zipf traces with skew parameters 0.9, 0.99, and 1.2 are used in the evaluation. In addition, real Wikipedia traces are used. Hit rate comparison compares COT to LRU, LFU, ARC, LRU2, and LHD. Load imbalance and front-end caching overhead comparisons compare COT to LRU, LFU, ARC, and LRU2. Finally, we briefly present a dynamic resizing experiment. Using Wikipedia traces, we show that COT outperforms LRU by 23% to 84% at different cache sizes, and outperforms LFU at 14% to 51% at different cache sizes. COT outperforms ARC by 9% to 42% at different cache sizes. COT outperforms LRU2 by 37% to 58% at different cache sizes. COT outperforms LHD by 4% to 24% at different cache sizes. And finally, COT achieved almost as good as the theoretical perfect cache. For the caching server load imbalance, we use Zipf 0.9, 0.99, and 1.2 distributions. Without front-end caches, the initial load imbalance is much higher than the target load imbalance of 1.1. This table shows that COT achieves the same load imbalance targets as LRU, LFU, ARC, and LRU2, with 50% to 70% less cache lines. This experiment determines the front-end caching overhead using different workload. We deploy a cache of 512 cache lines using different replacement policy and measure the overall running time when no front-end cache is deployed and when a front-end cache that uses different replacement policies is deployed. As shown, for uniform workload, front-end caches have almost no performance implications. However, as the workload skew increases, having a small front-end cache significantly reduces the latency. Notice that as the workload skew increases, the overall running time significantly increases when no front-end cache is deployed. This is shown by the red arrows. This increase in latency is solely because of the caching server load imbalance. Finally, this experiment shows how COT reacts to changes in workload. We divide the time into epochs, and in each epoch, the target load imbalance is evaluated. We start with a very small cache and tracker sizes and a workload of Zipf 1.2. As shown in the left figure, COT first identifies the best tracker to cache ratio. Then COT doubles both the cache and the tracker sizes until the target load imbalance is achieved, as shown in the blue and the green lines. Then we flip the workload to a uniform workload. Once COT detects the change in the workload, it shrinks both the tracker and the cache sizes, as long as the target load imbalance is not violated, as shown in the right figure. To summarize, we present COT decentralized elastic caches for cloud environment. COT is suitable for small caches, skewed workload with mostly read access. COT outperforms the hit rate of LRU, LFU, ARC, LRU2, and LHD for skewed, mostly read workload. COT achieves server-side load balancing with significantly less cache lines than other replacement policy. Finally, COT is dynamically resizable when the observed workload changes. With that, I am very happy to take your questions. Thank you.